Okay, so we're beginning our discussion of gravitational waves, okay? And we have several tasks to do. We want to model the source of the gravitational waves, a binary pair of stars or black holes that are merging, okay? And so we'll do that. We'll treat that as an external problem, which we'll handle in a rather naive fashion, as a couple of masses orbiting one another, following the rules of Newtonian mechanics. We think that's terribly naive, but it's not so bad. These things, these stars are orbiting one another, and this will give us a good zeroth order idea about that. We'll have an estimate on how much they're accelerating and what the character of that acceleration is, and that will provide us with a source for the gravitational waves. Okay, now the experts, of course, do use supercomputing, okay, to imagine two real black holes or neutron stars orbiting one another. They treat the gravity relativistically, according to general relativity. Okay, they start accelerating in that environment, and then they solve the wave equation exactly. Okay, as the waves come out of the system, okay, eventually their amplitudes are small enough, okay, and space is curved little enough so that you can treat the gravity waves as a perturbation, and that's where we pick it up. We're going to be treating the gravity waves at all space-time points as a perturbation. And so we'll have some, we're not going to be quantitative, of course, but we'll have short calculations to do. We'll see how the thing works, and then from there you can go on and do a better job. That's fine. Okay, we observe the gravity wave far, far away. In the case of the first LIGO case, 1.3 billion light years away. Okay, and where linear gravity is really accurate, you're not worried about that in the least. Okay, you worry about description in the vicinity of the emerging black holes. You have to do a good job on that, that's for sure. Okay, and that's what the pros do. Okay, so in our preliminaries, we'll study linearized gravity with a source. We'll look at the polarization states of gravity waves, and we'll discuss the detection of gravity waves. So let's, they're separate problems that we want to understand, and we can understand them just on the basis of elementary general relativity that we've done, at least in an idealized fashion. Okay, I want to look at the polarization states of gravity waves. We've discussed that conceptually before, but now let's put some meat on that discussion, okay, and write down some equations and describe them quantitatively. Okay, so that's what we're headed for. So here's our equation that we want to understand. The wave equation on the deviation of the metric from Minkowski. With a minor change, I go from eta to eta bar. Remember, we'll review that definition, but we had h as a deviation of the metric from the Minkowski metric, and then we did a little bit of kinematics, make a slightly better choice of this variable because the wave equation was simpler for h bar than it was for h in general. In the long run, it's not going to matter for our application, but let's do things right, and then the simplifications will come later. Okay, and then this was true, but it was only true when I imposed the gauge condition. We call it the Lorentz gauge because it looks like what I do in electromagnetism. In the case I'm doing electromagnetism explicitly relativistically, so the divergence of h is equal to 0. H, of course, is symmetric because it's related to the metric in a definite way. Okay, well, I can solve this. Wave equation is solved, of course, with a running wave, e to the I k dot x. When I say k dot x, I mean the inner product of the 4 vector for the wave number for the wave and the position, like that. I like to write x dot k dot x and just leave all that stuff implicit, but it's really this contraction. If I have the indices downstairs, I'll have explicitly the metric here, okay, and that's of course critical, but I like abbreviated notation until I need those guts. Okay, so I put this into the wave equation. Okay, we've done lots of exercises like this in discussion of special relativity, and this is a solution. the wave operator hits the wave equation, it brings down 2 powers of k, which contract like this, okay? Right. I write the wave operator in Minkowski space as a gradient lower index, and a times the gradient upper index summed over. So when I hit the plane wave with a gradient, a k comes down with the index down, then the next k comes down with the index up. They're contracted, so I get a solution as long as k squared is equal to 0. And of course I learn again that the graviton is a massless excitation sharing this energy momentum relationship with the photon. One of the discoveries of the LIGO experiment was a test that gravitons are massless, that they travel at the speed of light through flat Minkowski space. Okay, and so that's what I say here. Oh, and then along the way here was a matrix A mu nu that carries the indices that describes the wave's polarization, and we'll get on with that later. Okay. So radiation, of course, comes from the source. Okay, and here's the Einstein equation linearized appropriately for a particular source. How do I solve it? Well, it's the same form of a wave equation that I had in electrodynamics, and I know how to solve it. It's done in the appendices to the textbook, for example. Look up Landau and Lifshitz or your favorite E&M book. Okay, and so H is then an integral over the source. Okay, Y. Okay, and each bit in the source is weighed by a factor of the distance to the source. So the little bit at Y is radiating to the point X. Let's imagine that T is isolated near the origin where Y is small. That's a good approximation. And so X minus Y is the distance from that bit to the far away observation point. Okay, and then T mu nu depends upon a time variable and a spatial variable, and the time variable is what's called the retarded time. It accounts for the fact, okay, that the bits of the source radiate to the point X at giving off radiation that goes at the speed of light, but the distance depends as I move around the source. Okay, so if I specify a time over here, okay, then different parts of the source radiate at different times to accommodate the fact that it's the distance x minus y that's between the point of radiation and the point of observation, and y is moving about. Okay, so I identify the retarded time. You write T sub retarded because it accounts for the time delay, okay, for radiation to get from the various bits of the source out to X. T sub r accounts for the fact that bits of the source that are further than X take longer to get there and are radiated earlier. Okay, so that's nothing special to gravity. That's true of just the inversion of the wave operator in general, and so I've shown that over here. Okay. Now, in my applications, this distance r, the magnitude of x, is much bigger than the size of the radiating source, and so I can pull. So this is common to all the points that contribute to the integral, and so I pull it out and let's say I put my origin of the coordinate system at the center of mass of the source. That's the distance r here, and I can pull it outside the integral, and then the integral is just an integral over the source. Typically, the speeds of the bits of the source are small enough that this replacement holds good for the duration of the extent of the source divided by c. So I can consider the source frozen when I do the integral, because the time it takes for radiation to get from one end of the source to the other end of the source is considered to be small. Okay, it's considered to be small. There are cases where you have to be a little bit more sophisticated than a statement numbers too, but not so in this application. In this application, I don't have any of those considerations. That can be consideration of phase and interference and things of that variety, but that's not the case. Not the case here, because the sources are so sufficiently small that the different delays of propagation across the source are not significant. Under these conditions, you can replace this distance by just the distance from the origin, and you can pull it out. And that's all I do. I just pull it out, and then the rest of the problem is done correctly. Okay, not that this is incorrect. This is just approximate. But as long as I have 1 and 2, okay, then I can do it, and it's routine. Okay, so it's routine. I keep the full T and dependence upstairs, because I'm going to be generating traveling wave, and the space and time dependence of the traveling wave are inside that argument there, right? As we'll certainly see as we go, and that's stated over here. Okay, I pull the factor of R out. Okay, inside the integral, I can replace x minus y with R. With R itself, because x is so large. Okay, and I convinced myself there are no subtle effects with interference, and so there you have it. So what do I read off here? I read off that the polarization character, the tensor character of my source, determines the tensor character of my wave. Okay, and I see that my wave falls off like 1 upon R. It becomes gradually weaker as I move away from the source, and let's put a parenthesis there where it belongs. Okay, and there you go. One of the things that's interesting here is that our experiment and our detector will be sensitive to H, and H falls like 1 upon R. That's really very favorable, because if you're doing optical astronomy, of course, you're sensitive to the intensity of light coming, and the intensity of light falls off like 1 upon R squared, right? It goes like, it's second order in the electric field, for example, and the magnetic fields. Okay, so you lose another factor of R if you're doing stargazing compared to if you're doing gravity gazing. Okay, but the trouble is, of course, the right-hand side here is characterized by very small numbers, and so the amplitude is small. But if you improve the quality of your detector, your sensitivity over a region of the cosmos goes more rapidly than it does if you're doing optical telescopes. Okay, a 1 upon R compared to 1 upon R squared. So that's helpful. Okay, now so there you go. So that's good. We're set to go. I make a model of T mu nu, and I can get your H bar mu nu. Okay, but let's see, in H bar mu nu, well, that's a plane wave, and it has a polarization attached to it. So we want to understand that polarization a bit. This is the object that we discussed qualitatively when we were comparing special relativity and electromagnetism and general relativity, and we'll cover that ground again now, except with lots of formulas. I need to understand A mu nu. Okay, here it is. Okay, well, the first thing I know is I choose the Lorentz gauge. I have to do that to get a simple wave equation. The Lorentz gauge says I hit this thing with a gradient that brings down a factor of k. So I learned that k contracted into A has to be 0. Okay, and that's one of the constraints it has to satisfy, and I'll think about other constraints as I go. Okay, well, A mu nu starts out as a symmetric 4x4 matrix. It's symmetric, so it doesn't have 16 independent entries, it has only 10. But it gets chopped down a great deal because it satisfies the Lorentz condition. There are 4 conditions there, right? K has 4 components. So that gives me 4 conditions. That reduces the number of independent entries down to 6. Progress. But now we also remember that our our system of equations are made to have they're invariant to coordinate transformations, and in particular, if I'm looking at this weak field discussion, this weak field specialization, I specialize to infinitesimal coordinate transformations. That's the only ones I'm allowed to make to keep H small. So I have the transformations, we discussed them before. I'd make a transformation from x to x prime, and the deviations, component by component, are small. Chi is on the order of h, okay? But otherwise, a general function, just a small amplitude. Okay, so I can do that for each of the 4 variables. That brings in 4 more parameters, chi, mu, for mu running from 0 to 4. That gives me 4 more things to play with, and that reduces the number of independent entries from 6 to 6 minus 4, which is 2. Okay, so we have only 2 independent entries. Well, that reminds me of our general equation, our general discussion of the polarizations of gravity waves and our polarization of electromagnetic waves. We discussed in the case of electromagnetic waves that there are just 2 polarization states, okay, corresponding to the 2 Lorentz invariant states that we can make of a spin and a wave vector traveling at the speed of light. The spin could be aligned with it or against it. Those are Lorentz invariant configurations, giving us 2 polarization states for the photon. And the same idea applies to gravitons. Okay, there are only 2 states, and we're going to get those 2 states. Okay, that's just argued on the basis of simple kinematics. All this formalism includes that kinematics, so we're going to rediscover it. Okay, and so that's what I say here. We recall from our earlier linear gravity discussion that G was eta plus h. Okay, and under the transformation, an infinitesimal general coordinate transformation, G transforms. Okay, eta does not, it's a Minkowski metric, stays the same, and H transforms, and we learned that H transforms by this change, which is a gradient applied to chi, symmetrized, of course, because H mu nu has to be symmetric, it's a component of a metric. Okay. We went to the variable h bar, which differed from h by a term that was proportional to the trace of h. Okay, and then we make this transformation here. Okay, just plugging away. Okay, and then I see that h bar differs from h bar prime differs from h bar by again this gradient, symmetric gradient applied to chi, plus an additional term that goes like the divergence of chi, coming from the fact that h bar differs from h by a tracing operation. Okay, a trace. So I have this term in particular. Okay, and so then what I'm interested in is what happens to the Lorentz gauge under this change of a coordinate system. And here's what happens. I take the divergence of both sides. Most everything cancels out, but I end up with the wave operator applied to chi. Okay, so what I want to do here is to choose chi to be, for example, to be a solution of this wave equation, and then my h bar will achieve the Lorentz gauge. This is similar to a discussion you make in electrodynamics. You never need these, or very seldom need these gauge transforms, but you just need to assure yourself that you can always choose them to get back to the Lorentz gauge if you ever were foolish enough or had to, for some reason, consider a different gauge for the electromagnetic field. Okay. Okay. If we have a choice of the gauge transformation, where I can pull a polarization vector out and have a plane wave left behind, okay, then the H prime transformation law reduces down to this. I can then see with this plane wave, then I can take all of these derivatives in here, right? So I put in for H bar prime, I put A prime mu nu plane wave, and similarly in here, H mu nu plane wave. I evaluate these things for a plane wave, and that's my transformation law then for the for the gravity wave when I make a coordinate transformation. Okay. So now let's implement these two symmetries, Lorentz gauge condition and the transformation law for the gravity wave under small coordinate transformations, and see that I can get down to a very simple a mu nu, which I can interpret easily. So I'll consider a gravity wave going in the z direction. So k mu is k, 0, 0, k. 0th component, 1, 2, 3, okay? Engineered so that k squared is equal to 0. And I usually write k as omega over c in conventional optics fashion. Okay, and so then I'll write down these expressions for this particular case. You see now, so I have these specific k's to choose. So for example, if I look at the 0th component, 0, 0, 0, 0, 0, 0, 0, 0, okay, then I'll get these things contributing here, okay, and it all boils down that k prime 0, 0 is related to k 0, 0 by an addition of this particular term, okay, and then similarly with the other ones, okay. In particular, if I have 0, 1 over here, 0, 1, so I put 0, 1s over here. Well, remember, k1 is equal to 0, okay? And also eta 0, 1, that's the Minkowski metric, that's equal to 0. And so the only contribution I get is from the case where, okay, where let's say mu is equal to 1 and nu is equal to 0. So I get a k epsilon 1. So I have these bits to take care of, and I write them all out. Okay, so take a moment and check my arithmetic. I'm just plugging into this thing, nothing very fancy, and I just look at them, and I see I can choose various of these components to be equal to 0, right? If I choose epsilon 1 properly, that only appears in one of these characters. I certainly can choose a prime 0, 1 to be 0. I can match this against this and get 0. So that's my game. That's my game. Okay. And then also I write down the Lorentz condition. That was this. Okay. For the case of k being in the z direction, and so I learned that the third component is the same as the 0th component for a. Just plugging that in there. Right, you see it pulls off those components there. I know also that a is symmetric, and so that really simplifies everything down. So then I choose the epsilon to make those fellows 0, as I said. I'll also look at those equations. I can choose a 1, 1 prime to be equal to a 2, 2 prime minus a 2, 2 prime. Okay, and I can write these equalities, which then propagate through and make my first row, my first column 0. It's symmetric, so those are guaranteed to be 0. Okay, so I choose a11 to be minus a12. I'll call that little a, 1, 1. It's symmetric. I'll call that bb. And everything else is 0. You see, we're able to choose all of those other 0. So in fact, this big polarization vector for the gravity wave is really kind of easy. It has 2 degrees of freedom, either A or B. It's transverse and it's traceless. Okay, traceless. The trace is 0, A minus A 0. Okay, and it's transverse in this sense. Okay, and so I write A mu nu transverse traceless. Okay, and I'm not going to write it as a 4 by 4. I'll just write it as A. Okay, times the 4 by 4 tensor that picks out this component and this component. So E sub 1 is just 0 everywhere, except where you see a 1 here and a minus 1 here. And then similarly with B. I'll put the B term in by running B times a particular tensor, which has all zeros, except off diagonal 1, off diagonal 1, like that. Okay. So there you go. Now you know how to write it down, and you have an explicit justification of the argument based on relativistic invariance of the state of a graviton, because it moves at the speed of light, of having just 2 degrees of freedom. Okay. We can compare that to what happens in electrodynamics, and let's do that just as a matter of review. In electrodynamics, we had a 4-vector A, and it was divergence-free by the Lorentz condition, and we formed the field strength tensor by this 4-dimensional curl. If I take a plane wave, then A looks like this. Okay. Outside of the source, it satisfies the wave equation. That means that k dot k is equal to 0, just like the gravity case. If I choose k to go in the z direction, then the Lorentz condition tells me that k dot and epsilon is 0, tells me that epsilon 0 is epsilon 3, very much like what I did for gravity. Okay. Okay. Under a gauge transformation, I know how that works in electricity and magnetism. A changes by the gradient of a gauge function, like this. Okay. Okay, and so the divergence of A transforms by the wave operator applied to the gauge function, right? Just apply divergence to this fellow, you'll get div here, which is del inversion. So to get Lorentz condition as a result, just choose that the gauge function should satisfy this wave equation, and you can always solve that wave equation. It's a property of differential equations, second-order differential equations. Let's see, if I want to apply this practically in a case, I'll take my gauge function to be a scalar function times a plane wave. So I can implement this and implement it for the plane wave solution. I'll choose a plane wave gauge function. A gauge function can be completely general. This is simple. Okay. And then I'll make a gauge transformation like this. Okay, and so I get an extra term like this. I write it down for the 0th component. Okay. Okay, and so I can make epsilon prime 0 to be 0. Okay, so at this point then, I can use the gauge invariance and the choice of the Lorentz gauge to get rid of the 0th and the 3rd component of the polarization vector. That means that A is purely transverse, like this. Okay, and so the polarization vector of the traveling wave can be written as a linear superposition of 2 linear polarized states, where E1 mu just means 0, 1, 0, 0. Okay, for this E1. Okay, and for E2 be 0, 0, 1, 0. Okay, so I have just 2 linear polarizations indicating a transverse electric field for a field which is propagating in the z direction. Hopefully that sort of thing is not new to you, but there it is, and it's written down in the supplementary lecture. So check on the details, make sure you're comfortable with it, and maybe a little bit unfamiliar, but it's easy. So I think you can master it, and then you can see the generalization to the graviton wave, and understand now the polarization states of the 2 propagating waves. And next we want to discuss how to detect these waves, and we'll do that starting next time.